All right. So hello, everyone, and thanks a lot for the introduction. And my talk today is gonna relate to the good old saying, if all else fails, read the instructions. And that certainly applies to the problem of database parameter tuning, because a system such as a Postgres often have hundreds of tuning parameters. You see some of them on the left-hand side of the slide. And that creates the problem of how we can find optimal parameter settings in order to optimize performance for a specific workload and for a specific performance metric such as throughput or latency. And of course, in order to find those parameter settings, what you could do is just starting to try out random parameter settings, observing the performance that you're getting in a trial run, and over time learning from that to select better parameter settings. But probably it would be a better idea to first have a good look into the manual and perhaps also associated text documents like forum discussions about database performance on the web or blog entries about how to optimize the database for one specific scenario and so on. And in this talk, I'm going to transfer this generic piece of advice to the domain of automated database parameter tuning, because in this domain, current tools typically only learn from trying out parameter settings and observing the performance, whereas the system that I'm about to present, called DB-BERT, first of all analyzes all of those text documents in order to extract useful recommendations for tuning, and then it uses that as a starting point in order to explore parameter settings via trial runs. Up until a couple of years ago, this problem setting might have been overly ambitious. But fortunately, there has been significant progress in the domain of natural language processing over the past couple of years. And even if you're not working in natural language processing, you might have come across headlines like the ones that you see here, which discuss recent advances in natural language processing. And those advances are primarily due to two ideas. First of all, the transformer, which is a novel neural network architecture that, among other advantages, makes it easier to parallelize training. And that has in part enabled the creation of a very large neural network models for language processing with often hundreds of billions of trainable parameters nowadays. In order to train those models, of course, you want to have a large amount of training data. And here the second idea comes into play, transfer learning. Now, the idea of transfer learning is to execute a pre-training phase of the neural network with a problem for which large amounts of training data are easily available. And then we can at least partially transfer this knowledge by fine-tuning for more specialized problems where perhaps little training data is available. But because we can transfer a lot of knowledge, we don't need that much training data for specialized problems in order to get very good performance. For instance, one common pre-training problem is the problem of predicting continuations of sentences that we find on the web. And for that problem, of course, we easily can get lots of training data simply by sampling sentences. And when training such a large language model with that training data, then we should get something which has a certain sense for natural language understanding in general. And then, and that works very well in practice, we can fine-tune those models for other problems such as translating natural language questions into SQL queries. And due to the pre-training phase, even with relatively small amounts of training data, you typically get very good performance. And in fact, the newest generation of those models, which includes, for instance, the GPT-3 model, they often don't even need this fine-tuning phase anymore. They don't even need task-specific training anymore. Instead, you can just describe the task that you want to solve as part of the text input that you're providing to the model, the so-called prompt. I've prepared a little demo for that. Here I'm using the GPT-3 model, and I'm copying a text from the introduction of the Microsoft Wikipedia article. So I'm using this for text analysis. I'm copying this to the GPT-3 playground. And now, without training it specifically for that task, I could, for instance, ask it to extract information from the text that it has above. For instance, who is the CEO of this company? And now it extracts that information. Otherwise, what I could also do is, for instance, to summarize this text. Here I wanted to summarize all that text above in only 3 sentences. And again, I don't need to specify any specific training data for that. Instead, I just specify what I want to happen as part of the problem input. Summarize this in 3 sentences. And now here you see it generates a pretty reasonable summary of the text above. And as I have requested in the problem input, this summary contains exactly 3 sentences. Actually, right, 3 sentences. Now I'm also asking another high-level question, which relates to the text content, but that is not information that can be easily summarized or extracted. Should I give a talk at this company? And if so, why? And you see here, even for this question, which is a little bit particular and probably not part of any standard training benchmark, it generates quite a reasonable reply based on the text that it finds before. So this is just for showing a little bit the capabilities of this latest generation of language models, GPT-3, which I will be using in one of the projects that I'm about to present next. Now, I'm applying text analysis capabilities like the ones that we have just seen to text documents like the ones that you see here. Those are text passages taken from the online manual of Postgres, for instance, from discussions about database performance on forums such as DBA Stack Exchange, or from blog entries about a database performance that discuss how to tune a system in specific scenarios. From such text passages, I specifically want to extract text snippets like the ones that you see here, which recommend one specific value for one specific parameter. For instance, in the first case, we have a recommendation for the shared buffers parameter, which is relative to the total amount of main memory that is available on the tuned system. The second recommendation recommends an absolute value, and the final recommendation is a little bit specific because it does not explicitly mention the parameter that it actually refers to. So we have to know that if somebody wants to tune the parallel workers, probably the person is interested in a max parallel workers parameter of Postgres. Now, in order to exploit those tuning hints, DB-BERT translates them first of all into arithmetic formulas in order to use them for automated tuning. So here we have arithmetic formulas. Some of them are relative and contain factors that represent system properties such as the amount of available RAM. But if we know those properties of the system that we are tuning for, then we can resolve those recommendations into concrete values. And this is what the system is doing. Now, the DB-BERT system relates to other automated tuning tools because it takes as input a workload to optimize by changing the parameter settings and an optimization metric such as latency or the throughput of your workload. What makes it specific is that as additional input, it takes a collection of user-specified keywords, which could, for instance, describe the system that you're tuning on or relate to your tuning goals or to properties of the workload. Now, those keywords are used by the system in order to retrieve documents that are probably related to those keywords. And it does that by using the Google Search API. So it automatically downloads documents that relate to those keywords. Of course, the recommendations that we find on the web, they're not always reliable, and they may not apply to the specific scenario that we are currently interested in. In order to resolve that, DB-BERT executes live trial runs with a database instance and a sample workload in order to benchmark the performance that we are getting with specific parameter settings. And that gives it the possibility to validate and to mix and to adapt those hints that it finds on the web. After a user-specified timeout, the system returns the best parameter settings that it has found so far. And in order to get there, it internally executes 2 phases in each tuning session, a pre-processing phase followed by a learning phase, and I will discuss both of them in more detail in the following. Now, the goal of pre-processing is first of all to analyze the input text documents in order to extract hints, meaning recommendations, to translate those hints into arithmetic formulas like the ones that we have seen, and also to order those hints in order to determine in which order those hints are considered for trial runs in the following phase. Now, more precisely, here we are starting from a collection of text passages that have been extracted from the web, which may or may not contain tuning hints. The first goal is to detect the parameters that those passages refer to. And that can be easy if the text passage mentions the parameter names explicitly, of course. But in some cases, it can be more difficult if you only find a vague description that points at which parameter to set. And then you need to compare the text to the names of the parameters of the system you're tuning for in order to identify the most likely parameter it refers to. Now, having detected parameters, the next step is to extract those arithmetic formulas that we have seen before. And finally, once we have those formulas expressing the recommended value for specific parameters, we can resolve those formulas by inserting the actual properties of the system you're tuning for, like the amount of RAM, for the placeholders in the formulas. And the end result of all of this is a collection of hints which assign specific parameters to a specific concrete value. And by the way, the first two of those steps, they use language models. To make it a little bit more concrete, let's have a look at a simple example. So here we have multiple passages that contain useful tuning hints. Now, the first step would be to extract the parameters that they are referencing. That is quite easy for the first three of them. In the last case, it requires reasoning because the name of the parameter is not explicitly mentioned in text. Now, in order to get recommendations for those parameters from those text passages, the system executes actually two sub-steps. First of all, it tries to identify which part of the input contains the specific recommendation for a specific parameter, because the same text passage can talk about multiple parameters. The second step is to translate this into an actual formula, which may contain placeholders, which we still need to resolve by replacing them with actual system properties. And then, as you see here, we get to concrete value recommendations for all of those parameters. So the main result of the pre-processing phase are those hints which assign specific parameters marked in red to specific values. Finally, it uses a simple heuristic in order to determine the order in which those hints are considered, prioritizing parameters, hints about parameters that are frequently mentioned, while avoiding considering too many hints about the same parameter. Now, this forms the input to the learning phase. And the goal in the learning phase is to figure out how to adapt those hints that we find in text, meaning that the system can choose to deviate a little bit from the recommended values in order to specialize to the current tuning scenario. Another thing that it needs to figure out is how to prioritize hints, because often the hints that we find on the web, they might conflict with each other, and then it becomes important to figure out which hint to prioritize, or whether to try to somehow make a compromise between hints that you find from different sources. And then also, finally, the goal is to aggregate multiple adapted and prioritized hints into combinations of parameter settings that the system can evaluate in trial runs. Now, the way learning happens is essentially by trial and error. The system in the learning phase, until the time runs out, it will select parameter combinations, parameter settings to try out and to evaluate via those trial runs in order to benchmark performance. And now we have a choice, because we iteratively select those parameters settings based on previous experiences within the same tuning session. We can either choose to explore parameter settings that are somewhat similar to parameter settings that we have tried before. That would be exploitation. Or we can decide to explore parameter settings that are very different from what we have seen before, and that is exploration. And it is very important, because otherwise we might get stuck in local optima. Now, the most principled framework in order to resolve this so-called exploration-exploitation dilemma, that is reinforcement learning, and this is the framework that I'm indeed applying here for the learning phase. And in reinforcement learning, we generally have an agent which interacts with an environment. And the agent can influence the environment by so-called actions. On the other side, the environment returns observations to the agent, which help the agent to figure out which actions to take next. Also, the environment returns rewards to the agent, and the goal of the agent is to maximize the accumulated sum of those rewards it is collecting. But of course, initially, the agent does not know how the environment works, so it needs to figure out over time which action sequences lead to maximal rewards, and in order to do that, it needs to solve this exploration-exploitation dilemma. Now, mapping this generic scenario to the specific scenario that we have here, the agent that corresponds, of course, to the DB-BERT system. The environment is characterized by workload and system properties, and actions allow the agent to adapt hints, meaning to deviate from recommended values, to prioritize between different hints, and to aggregate hints in order to evaluate them in trial runs. Observations are based on the text of the tuning hints that the agent collects. And there are two components to the reward function. First, the small reward is already attributed to the agent for trying out parameter settings that are accepted by the database management system. Because perhaps when misunderstanding a recommendation or when using a recommendation from a bad source, then the resulting recommended values might be outside the admissible value range for that parameter. In this case, the database management system will reject those settings and the agent gets a negative reward. Then on the other side, of course, we are interested in maximizing performance according to the user-specified performance metric. So whenever the agent executes a trial run, it will get a performance-related reward, which simply is proportional to the amount of improvement compared to the default parameter settings. Now, this is the high-level setup of the learning scenario. In order to make it more concrete, let's continue with the example before. Here we have collected a tuning hint that recommends specific values for specific parameters. So now the agent needs to figure out how to adapt the recommended values by multiplying them by certain factors, and how to assign priority weights to those hints if some of those hints are in conflict with each other. After selecting how to adapt recommended values and how to prioritize different hints, we can aggregate this into one configuration, meaning setting for some subset of parameters that can be evaluated in a trial run. And just to be sure, this upper part of the matrix, that one has been generated during pre-processing. It does not change anymore over the course of the tuning session. The lower part of the table, that has been generated by reinforcement learning. So this will continue to change during the tuning session until time runs out. The agent will try out different values for those parameters, which lead to different configurations that it can evaluate. Now, in order to give you a little sense for what it's like using this system, I have a quick demo here, and you find the source code for this demo on my GitHub repository. So what you see here is the interface of the DB-BERT system. And as it uses text input, the first step is to select a collection of text documents that should be used for tuning. And here I'm using the Postgres 100, which are essentially the first 100 web documents you get for the Google query Postgres performance tuning. And I have already downloaded those documents using the automated tool that is also in the repository. In order to enable the system to resolve relative recommendations, I need to tell it about the hardware properties of the system to optimize for. And I need to provide it with access credentials in order to be able to do trial runs with a live database instance. That's what I'm doing here. And finally, I need to select a tuning metric here between a runtime and throughput. I'm selecting a runtime, and I need to specify the workload to optimize for. Here, this file contains actually TPC-H queries. So now everything is set. Now tuning starts by clicking on this button, and it takes about half a minute in order to do the pre-processing, and the result of pre-processing is here. So this is a table which contains detected tuning hints together with their formal representation. So here the system has found the text passage which recommends setting shared buffers to 25% of available RAM. the system has correctly inferred that shared buffers is a parameter that is mentioned in there, and the system has correctly inferred that the recommended setting for this parameter is 25%, and that is relative to the amount of main memory. Now, based on those hints extracted during preprocessing, the learning phase starts, and here the system assigns first of all factors in order to adapt the recommended values. Here, for that hint, we decide to multiply by a factor 0.5, basically. Also, the DB-BERT system chooses weights to represent the priority of this specific hint. And here in the accepted column, you see whether the database management system has accepted those this recommended value. That was the case. This is why the system already obtains a small assignment reward of 10 points. Now, the last column here represents the performance reward, and I mentioned that they are only awarded if the agent performs a trial run. Now, the agent will not perform a trial run after each single hint. Instead, it will make decisions for a group of hints and then finally make a trial run. This has happened here, as you see, and it's a positive reward, which means that performance seems to have improved compared to the default configuration. Now, the table that you see above contains more information about those trial runs. You see in particular the performance column, which in this case represents the execution time for the TPC-H queries. And as you see here, just within a few minutes of tuning time, the system has improved performance from 24 seconds to something like below 18 seconds. So we have made significant progress within a very short time frame because the system was able to mine interesting information from text documents.
Emmanuel, do you always during this preparatory phase, do you always get the all the parameters that are necessary in order to initialize, or do you have cases where a lot of the parameters are just not set because there was just not enough information in the documentation, or and you just end up having to have default values or whatever? What's been your experience so far with it?
So, okay, that is a great question. So I mean, typically during database tuning, only a subset of the parameters are changed compared to the default settings. So a recent work, also there was this 21 paper by CMU, which experiments with actually industry workloads. And you also did focus on a few parameters where they changed the value compared to the default settings. And that is the case here as well. So certainly not all parameters are typically changed during one of those trial runs. Instead, it focuses on a few tens of parameters at most typically. And that is consistent with what other automated tuning tools have done. However, having said that, it does not restrict the search space to those a few parameters a priori. The system considers the full search space of hundreds of parameters, for instance, for Postgres and MySQL. In order to narrow down which things to try, it uses those text documents as input. And the assumption is a little bit, if one parameter was never mentioned on the web for a relevant Google query, then probably that parameter tends to be less important for performance. So,
I see. And do you accumulate knowledge about which parameters the performance is sensitive to which parameters, and so that guides you in tuning other databases? I mean, that is there sort of learning across multiple sessions?
That could be a very interesting extension, absolutely. I mean, for the moment, the system only learns within a specific tuning session. The assumption is also that you could provide a description of the specific tuning scenario that you have, which would enable the system to retrieve different documents in order to get a good starting point for a reinforcement learning-based tuning. At this point, I'm not transferring knowledge between different instantiations of the system, but that would be a very interesting extension indeed.
Got it. Thank you.
Great questions. All right. So this was a quick demo of the system with the Postgres database management system. I experimented in different scenarios focusing on Postgres and MySQL and on benchmarks such as TPC-H and TPC-C. And here I'm only going to show a little extract from those experiments. We've seen a little bit of Postgres. So in the following, I'm going to show primarily MySQL. The input text that I'm going to use in the following are the first 100 documents that you get from running the Google queries Postgres performance tuning and MySQL performance tuning. And on the lower part of the slide, you already have a couple of statistics about those documents. On the x-axis, you have parameters ordered by the frequency at which they are mentioned in those documents. And clearly, there's a couple of parameters, such as shared buffers for Postgres, that are mentioned with a much higher frequency than other parameters. So the baselines that I'm comparing against in the following are, first of all, baselines that purely use reinforcement learning. So those baselines essentially try out things as they go, starting pretty much from scratch from random initializations. And then they use reinforcement learning in order to converge to good settings over the course of a tuning session. The other type of baseline that I will consider in the following, and that's a baseline that I have proposed in another recent paper, only uses in text in order to make a tuning decisions. So it will just extract tuning hints from text and then use whichever of those hints are mentioned most frequently in case of conflicts. Now, both of those baselines don't work that well. Oh, I think there was a question.
I think somebody just didn't have their mic muted.
Was there a question? Oh, okay.
No, I don't think so. I think someone there was some background conversation by someone who didn't have their mic muted.
Okay, fair enough. All right. So here I'm comparing different automated tuning tools in order to optimize MySQL for TPC-H. And on the x-axis, we have tuning time. On the y-axis, we have execution time for TPC-H queries of the best parameter settings found until a certain point of tuning time. And DB-BERT, that's the line marked in red, and as you see here, it relatively quickly finds interesting parameter settings that lead to significant speedups. Whereas the other baselines, for the purely reinforcement learning based baselines, they have less information to work with because they don't access information in text. The keywords and supervised baselines only extract information from tuning text and cannot validate that information or specialize it for the current tuning scenario. And this is why they also perform significantly worse compared to DB-BERT. And the tendencies are similar for benchmarks such as TPC-C. Here the y-axis shows a throughput, so higher is better. And again, DB-BERT finds interesting parameter settings relatively quickly because it is able to extract more information as a starting point. In the paper, you find experiments with more diverse text, with more benchmarks and baselines and systems. And in this presentation here, I've only shown a little extract of that. So in summary, DB-BERT uses text analysis in order to extract tuning hints that form starting points for automated parameter tuning. And compared to reinforcement learning, pure reinforcement learning, it has a better starting point. Compared to pure text analysis, it has better abilities to adapt to the current workload. And because of that, it tends to find promising parameter settings faster than those baselines. Another thing, which is harder to quantify with experiments that might nevertheless also be important to users, is that DB-BERT, since it only uses tuning options that are somewhat related to text snippets that it has found, it can give users more explanations about why it has tried out specific parameter settings by linking suggested changes to the default configuration to specific text snippets that have motivated them. So DB-BERT is a first project which exploits a parameter, which exploits text analysis in order to tune existing database management systems. But I'm wondering whether it's not possible to enable a novel database management system architectures by exploiting those language models as well. And in the following, I'm going to present first the very initial results of a new system called the CodexDB. There's an upcoming paper at the VLDB at 22. And the goal of CodexDB is basically to enable a customization in data processing via natural language instructions. So more precisely, users will provide an SQL query along with some natural language instructions about how this query should be processed internally. And then the system internally generates a code for processing this query, which should implement the natural language instructions provided by the user. And in the end, it returns the query result to the user along with the generated processing code. Now, I can see at least two use cases for this. First of all, having a system which can be easily personalized for lay users who may not know how to code. For instance, those users might want to generate non-standard output during query processing in order to help them debug their SQL queries. And with the system, they are able to specify natural language instructions describing which output they want to generate. And then if everything works well, the system can implement that. But also for more experienced developers, it might be interesting to use such a system, for instance, for rapid prototyping. When planning to try out a new processing strategies for SQL queries, as a first step, it would be very convenient to describe that strategy in natural language in order to get some first performance results and then decide whether to implement a full system based on that or not. The technology which enables such a system, that's the GPT-3 Codex model. That is a very recently released model by OpenAI based on the GPT-3 model, but focused on synthesizing code in different programming languages from natural language instructions. So the model is quite flexible, but perhaps the primary use case of the model is to have an input, a prompt, which essentially corresponds to a natural language description of what you want to implement. And then the output of that is code which actually implements those instructions. I'm using this system for CodexDB. Now, before we can customize anything, first of all, we have to be able to generate code which actually process specific SQL queries. And the most straightforward way of using GPT-3 Codex for that task would be the one that you see here. So what I'm doing here is essentially, first of all, to generate a natural language description of the database schema by exploiting information from the database catalog of CodexDB and some simple text templates to translate this information into text. Then the resulting prompts can be submitted to GPT-3 Codex and the resulting code can be executed. Then the result is returned to the user. Now I have tried this approach. I'm going to tell you a little bit more about the following. First of all, let's see one example for one of those prompts. What do they look like? Here, that is an example prompt. And you see here marked in yellow, we have like information about the database schema. Marked in green, we have information about the physical location of the associated data. And marked in red is one example query that should be processed. And marked in blue, those are some subtle indications for GPT-3 Codex about which programming language the generated code should be in, because GPT-3 Codex can generate multiple different programming languages. Here, this is a subtle reference to Python, because that is the language that the system is currently known to be most proficient in. This is why I used this as a starting point. Now, first of all, in order to try this out, I need benchmarks, and perhaps the most related problem to generating code from natural language instructions for SQL queries, that is the problem of generating SQL queries from natural language questions. And that is a problem where there has been a lot of work with lots of well-established benchmarks, such as WikiSQL, which contains relatively simple queries, and Spider, which contains more complex queries containing joins, for instance. And I'm using queries from those two benchmarks as input for the following tests, starting with WikiSQL. And I will consider a test case, a query, as solved correctly if the generated code produces the correct query result. And in the following experiments, I'm going to essentially give the system 2 tries. And if any of those tries generates executable code, then the first executable code that the system generates will be used in order to assess this success criterion. If none of the 2 tries generate executable code, then the test case is considered as failed. And just for comparison, in order to put the following results into context, for the corresponding text to SQL translation tasks, those 2 benchmarks, particularly WikiSQL, they already have some very powerful methods that solve them and reach a precision of north of 90%. Spider is more complex, so the precision on the current leaderboards is more something a little bit above 70%. All right. So first of all, I'm using the prompt that I have just shown, which is the most straightforward way of using this approach. And I'm trying with 2 versions of GPT-3 Codex, the Da Vinci version and the Cushman version. Da Vinci is the most powerful version of the model with most trainable parameters. Cushman is the second most powerful version. And when trying with 100 WikiSQL queries, it seems that not a single of those test cases is solved successfully. So clearly, we have to change something. Now, the problem seems to be that giving a GPT-3 like an entire query and expecting it to figure out how to process that in multiple steps might be asking for a little bit too much. But fortunately, in the database community, that's a problem setting that we have lots of experience with. We decompose complex queries into a sequence of simple processing steps by a process called query planning. And therefore, I want to apply those techniques in this context as well. Of course, I cannot directly apply existing query optimizers because traditional query plans are represented as trees. But in order to make them understandable for GPT-3, here rather we have to describe those query plans by a text description, and a text description has to be sufficiently high level in order to create room for customization by more commands from the user. This is how it looks like. I'm adding a query parser and a simple query planner, which produces an output text describing a couple of processing steps in order to get the correct query result. Now let's see whether that changes our success rate a little bit. And before I do that, here, one of those example prompts, it's the same query as before, but here the part marked in red has actually changed compared to the previous prompt. Whereas before I had a query, now I have a sequence of processing steps that have been generated by this natural language query planner. And that helps. So now we're getting up to 22% of successfully solved test cases using the most powerful Codex version. Of course, 22% is still not great. So we want to improve over that. And one way in which we can do that, typically for GPT-3 in general, is by integrating a small number, maybe 2 or 3 of examples into the prompt that we are submitting to the system, which is called a fusion learning. This is what I'm doing here. I'm integrating samples of successfully solved test cases into the prompt that I provide as input to a GPT-3. But of course, the question is, where do those successfully solved test cases come from? And I do not want to require users to solve those test cases themselves. That would be inconsistent with the use case for lay users that I mentioned before. Instead, I want to generate those successfully solved test cases automatically in an admittedly expensive pre-processing stage. So what the system does in this pre-processing stage is, first of all, given a sample query that is somewhat representative for the workload or a few collection of them, to use a traditional database management system in order to generate ground truths for those queries, meaning query results. And then it will repeatedly use a GPT-3 with some degree of randomization in order to generate multiple code versions for that current query until it finds a first code version that is executable and produces the correct output. And if that is the case, then it is added to a library of code samples that can at runtime be used for fusion learning. So this is the architecture changes. Yes.
Can you give us a sense of what it means for it not to be executable? I mean, like what goes wrong here? I mean, are there
Right.
Can you characterize what it's doing wrong in some more abstract way?
Sure. I mean, so in general, I mean, if the code is not executable, it essentially means that the code comes back from GPT-3 Codex, and now the code executor tries to execute that code and gets an error message, basically. So it doesn't successfully execute. So it is easy to detect, and the reasons for why the code is incorrect, they are quite diverse. I mean, often the generated code is not far from a correct code. Sometimes the name of one variable is switched, for instance, or I mean, when processing tables, I noticed that GPT-3 often sometimes it removes columns too early from intermediate results, and then it cannot find them anymore, for instance. So it is typically, I mean, so it's, I mean, like in separation, like each line typically contains like a correct piece of code, but it's in the dependencies between those lines of code that things go wrong, and that happens more frequently if the generated code tends to be longer.
I see. I mean, is this something that's likely to improve? I mean, if they continue to work on it, that it's, I mean, this is just a weakness in an early version of Codex, or?
I think that's something that is likely to improve over time. Yes, they keep releasing new versions of GPT-3 Codex, and yes, it improves things. And I also think that there's like more extensions that I can make from the framework side in order to increase the chances of that. I mean, right now, for instance, one thing that I'm doing, I'm just generating like the entire piece of code. It might be, for instance, one possibility would be to generate parts of the code and then to provide a new prompt which summarizes the currently available intermediate results in order to resolve cases where there's like dependencies that are too long, for instance. But yes, there will be also improvements from the model, I'm sure.
Oh, I see. Thank you.
Sure. And now, speaking of improvements to the model, with this few-shot learning approach, actually, the ratio of solved test cases that we are getting here with the most powerful version actually reaches 79%. And now there's a huge difference to before. So you can see that just adding 2 samples in each prompt, which are randomly selected and automatically generated, actually brings us to something which is still a little bit below the performance of text to SQL translation methods, which is not 100%, but close to 100% on this benchmark, but still to something that is within reach, I would say. So sure, there will be further improvements, I'm sure, but I mean, for this relatively simple benchmark already, we're actually getting some pretty interesting results, I believe. All right. So, of course, the final piece is that we actually want to enable users to customize the code that gets generated, and they do that via natural language instructions. Fortunately, since I have generated those prompts which contain steps in natural language, integrating user-provided text instructions is relatively natural. If the user provides text instructions that refer to the generated code as a whole, for instance, let's use the pandas library, which is a library for data processing in Python. Then we can just put this as the first step in the processing plan. If the user has requirements about the output of after different processing steps, then we could, for instance, add corresponding user-provided text after each of those commands. So then having this possibility of customization, first of all, if we have customization commands, it kind of increases the constraints that the model tries to comply with when generating the code. So we can say that it makes things harder. And that shows up in the results here. So here now I'm presenting results for WikiSQL, but also for the Spider benchmark, which is much more complex and includes, for instance, joins. You see the success ratio on the y-axis, and on the x-axis, you see different customization commands very slightly shortened. For comparison, on the left-hand side, I have the results if we don't have any customization, no additional instructions. After that, the next 3 results are then asking the system to use a specific library for data processing, pandas, vex, and data table. The next 3 instructions are asking the system to generate specific types of output, ranging from just printing out done after each processing step, over printing out intermediate results, or printing some natural language progress updates. And as you see here, it has an impact on the success ratio. So there's definitely some room for improvement. There's a few commands that can actually even improve the success ratio. For instance, asking the system to use pandas slightly improves the performance on Wiki SQL, because that is a very natural library to use for SQL query processing as well. But in some of the other cases, the success ratio clearly drops. But more importantly, what we ultimately want from this is that a generated code implements those user-specified instructions. And here, there's actually good results on that, because 100% of the generated programs, they import the libraries that have been specified in natural language instructions, compared to only up to 30% of generated programs without further instructions. So in those 30% of cases, the GPT-3 model decides itself to use a certain library. In particular, that's the pandas library for processing. But clearly, those customization commands, they change the code as it's generated, and quite successfully so. Now, it is a little bit harder to say for those logging-based instructions, because for something like print progress updates, it is difficult to say that one progress update sounds better than another one. This is why I plan to integrate in future versions some kind of feedback mechanism from the user about like how well the currently generated code is following those natural language instructions. But at least when considering only the category of the print statements that the system decides to add in the code with close to 100% accuracy, the system adds print statements that are consistent with the natural language instructions. For instance, when asking the system to print out intermediate results, then almost all programs that are generated have some print statements that print out variables, which can be considered intermediate results. Or when asking the system to print out progress updates, it will include print statements that print out constant strings, which typically are derived from the natural language description of the processing steps, which makes sense. So finally, let me show you like one example of how the generated code changes by the instructions. I'm not going to go through this code in detail, but just from having a high-level look at it, on the left-hand side, we have code for a specific query generated without further instructions. On the right-hand side, we have code for the same query generated using the additional instructions, use pandas library. As you see here, those two pieces of code are quite different. They differ in terms of the libraries they use, they differ in terms of the length and so on, but both of them answer the query. All right, so in conclusion, I hope that I have shown that there are some interesting use cases for language models in the context of data management. I have presented two such systems. First of all, the DB-BERT system, which uses text analysis in order to mine tuning hints from text documents. And you can find the corresponding paper at SIGMOD this year. CodexDB is a project still in early stages, which aims at generating customizable code for processing SQL queries, and that customization happens by providing natural language instructions. I'm going to present the paper on that at VRDB. Finally, for both of those projects and a few others, you find the source code on my personal GitHub account, github.com/iTremor. And very finally, I want to invite you to the tutorial that I'm giving at VRDB 22 on language models and their applications in data management. It's either in Sydney or you can also attend virtually. Would be great to see you there if you're interested in those topics. And with that, thank you so much for the invitation and for the attention, and I look forward to your questions.